All right, let's do this. Big Bang time. We got a request to dive into the Big Bang Theory, and clearly you guys want to go deeper than just like the surface level stuff. So we're going to do it. We're going to unpack what the Big Bang actually says, like what it really means, and then look at the evidence, the stuff that makes it so convincing. And then, of course, we got to talk about the mysteries, right? Because what's a good deep dive without a few cosmic head scratchers?
What always gets me is that, like, think about it. We're trying to explain the entire universe, its origin story, and we're doing it based on real, tangible evidence. It's amazing how science can connect what we see today to events that happened billions of years ago.
Totally. And I think, for me at least, when I hear a Big Bang, I kind of picture, well, a big explosion, right? Is that even close to accurate?
Not really. I mean, that's a common image people have, but it's misleading. The Big Bang wasn't an explosion into space. Think of it more as space itself expanding, like the fabric of space stretching, carrying all the matter and energy along for the ride.
Okay, so you're saying everything, and I mean everything, was once packed into this tiny, unbelievably dense point. How is that even possible? It's kind of hard to imagine.
It really is mind-blowing, and that initial state, which we call a singularity, that's where things get really, really interesting and where our current understanding of physics kind of starts to break down.
I can imagine. Okay, so, like, how did scientists get from, the universe seems to be expanding to, boom, Big Bang? What's the big clue, the smoking gun?
Well, it's not just one thing. It's more like a bunch of observations from different areas of cosmology. It's like putting together a giant cosmic puzzle. We can start with Edwin Hubble. Back in 1929, he made a groundbreaking discovery.
Oh yeah, Hubble's law. He figured out that galaxies are moving away from us, and the farther away they are, the faster they're going, right?
Exactly. And he didn't just see this visually. He used this technique called redshift. Basically, the light from those far-off galaxies, it gets stretched, shifted towards the red end of the spectrum. And the more redshift, the faster the galaxy is moving away.
So it's like a cosmic speedometer, but using light. It's pretty clever. But how does redshift prove the Big Bang happened?
Well, think about it. If everything's moving apart, if you rewind that, everything gets closer and closer together, suggesting that at some point, way back when, everything was squeezed into a single point.
Okay, I see. So Hubble gave us the expanding universe. What else is there?
How about a faint echo from the Big Bang itself? We're talking about the cosmic microwave background radiation, or CMB.
I remember reading about that, but I got to be honest, it went kind of over my head. Can you explain it like I'm, 5?
All right. Imagine this. The Big Bang was insanely hot, and as the universe expanded, it cooled down. But that initial heat, it should still be detectable today as this really faint microwave radiation coming from every direction in space.
And that's what Penzias and Wilson stumbled upon back in the 60s, right?
Right. They were working on something completely different and picked up this weird signal. At first, they thought it was just interference, but it turned out to be something way more important. They'd actually found the afterglow of the Big Bang.
And that discovery earned them a Nobel Prize, didn't it? So it must have been a big deal.
Absolutely. And here's the really cool part. The temperature and how uniform this radiation is, it matches perfectly with what the Big Bang model predicts. It's some seriously strong evidence.
So we've got Hubble showing us the expansion, Penzias and Wilson detecting this leftover heat, and then what? What else helped make the Big Bang the leading theory?
Well, let's rewind back to that super hot, super dense early universe. Remember, the Big Bang wasn't just about expansion. It was also like a cosmic kitchen, cooking up the very first elements.
Oh yeah, now I remember. There's this abundance of light elements in the universe, like hydrogen and helium.
Exactly. And you know what? The Big Bang Theory actually predicts the exact ratios of these elements that should have formed in the early universe. And when we look at the composition of the early universe, the measurements match up incredibly well.
So we've got Hubble, Penzias, and Wilson, and now this element thing all pointing to the Big Bang. I'm starting to see why it's the leading theory.
It really is remarkable how all these different pieces of evidence come together, painting this consistent picture of how the universe began.
But even with all this evidence, there are still some big mysteries, right? I mean, what would a good deep dive be without them?
Oh, absolutely. The Big Bang model answers a lot of questions, but it also raises new ones, some really big ones.
Okay, so more Big Bang mysteries. Last time we talked about the evidence, right? The expanding universe, the cosmic microwave background radiation, that leftover heat, and then how the first elements formed, all signs pointing to a universe that started out super hot and dense and has been stretching and cooling ever since.
And like we mentioned at the end of part one, the Big Bang Theory is a huge success, but it also leaves us with some pretty big mysteries.
Yeah, exactly. Like, if the Big Bang created equal amounts of matter and antimatter, Why is there so much more matter? I mean, shouldn't they have canceled each other out, leaving just energy?
Right, that's the puzzle of baryon asymmetry. You see, the standard model of particle physics, it says matter and antimatter should have been created in equal amounts in those first moments of the universe. Kind of like if you had a bag of marbles, half black, half white, you'd expect to pull out the same number of each. But what we see is way more matter than antimatter.
So there had to be something, some process that tipped the scales, right? Gave matter the upper hand. Do scientists have any idea what that could be?
It's one of the big questions in cosmology. We call the process of baryogenesis, and it would have happened very early on in the universe's history. There are some theories, but actually proving any of them, that's a huge challenge.
Makes sense. So we've got this missing antimatter problem, but then there's this whole other mind-blowing thing. Dark matter and dark energy, stuff we can't even see, but it seems to make up most of the universe. I mean, how crazy is that?
It really makes you realize how much we still don't know, right? We've mapped all these stars and galaxies and planets, but it turns out we're only seeing a tiny part of the whole picture.
So let's break this down a bit, and I'm still trying to get my head around it all. Dark matter's pulling things together, but dark energy is pushing them apart. How does that even work?
It's a great question, and it gets to the core of how these two forces shape the universe. So first, dark matter. It interacts mostly through gravity. We can't see it directly, but we know it's there because of how it affects stuff we can see, like galaxies.
Right, like how galaxies spin way faster than they should if you only count the stuff we can see.
Exactly. It's like there's this extra gravity holding them together, and that's where dark matter comes in. It provides that missing gravitational pull. But then we have dark energy, and that's a whole other puzzle. Think of the universe like a loaf of raisin bread rising in the oven. For billions of years after the Big Bang, the expansion was slowing down, like the bread rising more slowly as it gets bigger.
Okay, that makes sense. Gravity's pulling everything together, so you'd think things would slow down, right?
Right, but here's the wild part. When we look at distant supernovae, those super bright exploding stars, they showed us that the expansion isn't slowing down at all. It's actually getting faster, like someone cranked up the oven temperature and the bread is suddenly rising much faster.
Whoa, seriously. So it's not just expanding, it's accelerating? That's crazy.
It is, and that's where dark energy comes in. It's this mysterious force that's acting like, well, like a cosmic accelerator pedal, pushing everything apart faster and faster.
So dark matter's like this extra gravity holding stuff together, and dark energy's working against gravity, pushing it all apart. It's like a cosmic tug of war.
That's a great way to put it. And here's the mind-blowing part. Based on what we've observed and calculated, dark matter and dark energy, these two things we can't even see, they seem to make up most of the universe's total energy, like the vast majority.
So everything we can see, the stars, the planets, all the galaxies, it's all just a tiny fraction of what's actually out there. That's kind of incredible and also kind of terrifying. Yeah.
I know. It really shows you how much more there is to discover about the universe. It's like we've only read one page of a huge cosmic book.
And this deep dive, it already feels like we've gone so deep, and yet we're just getting started. So what are the latest theories about these dark forces? Are we any closer to understanding what they actually are?
That's the million-dollar question, and it takes us to the cutting edge of cosmology. We'll delve into the current research and some of the candidates for dark matter and dark energy in part 3. Don't go anywhere.
And we're back. It's amazing to think we started with the Big Bang, and now we're talking about dark matter and dark energy, these invisible forces shaping like the whole universe.
I know, right? It's kind of crazy how scientists can figure out that something exists, even if we can't see it or touch it. But figuring out dark matter and dark energy, that's become like one of the biggest challenges in cosmology.
So where do we even start? What are some of the top theories about what these things could be?
Let's tackle dark matter first. One of the leading candidates is this hypothetical particle called a WMP, which stands for Weakly Interacting Massive Particle.
WIMPs, okay. So they're massive, which would explain the extra gravity, but what's the weakly interacting part about?
That's the key. WIMPs, they're thought to interact very weakly with normal matter and with light. It's like they just pass right through us all the time, barely leaving a trace, except for their gravity, of course.
But if they interact so weakly, how could we ever, detect them? Wouldn't that be almost impossible?
It's definitely tough, but scientists are using these super sensitive detectors, some here on Earth, some out in space, hoping to catch, a tiny flash of energy or light when a WMP bumps into a regular atom.
So it's like a cosmic game of hide and seek, but with particles. So WIMPs are one possibility for dark matter. Are there any other, contenders.
There are. Another interesting one is a particle called an axion. Axions are even lighter than WMPs, and they interact even less with regular matter, which makes them even harder to find.
Wow, talk about a challenge. So dark matter is a mystery, but what about dark energy? Any good leads there?
Dark energy is, if anything, even more of a mystery. One idea that's gaining some traction is that dark energy is just, well, a fundamental property of space itself. Remember Einstein's cosmological constant?
Vaguely, it was like something he added to his equations, right? Part of his theory of general relativity.
Yeah, that's it. He originally included it to try to make a static universe, one that wasn't expanding. But then Hubble came along and showed us the universe is expanding, so Einstein kind of dismissed it as his biggest blunder. But the funny thing is, that cosmological constant might actually be the key to understanding dark energy.
Seriously. So you're saying space itself just has this built-in energy, like a built-in expansion mechanism.
That's one way to think about it. The cosmological constant, it would mean that space has a certain energy density, and as space expands, the total amount of that energy increases, which would drive the acceleration we're seeing.
That's pretty wild. Are there any other theories about dark energy?
Oh, yeah, definitely. Some scientists think dark energy might not be constant, that maybe it's changing over time, or even interacting with dark matter. There are even some modified theories of gravity that try to explain the accelerated expansion without needing dark energy at all.
Wow, so many possibilities. It really makes you wonder what kind of crazy discoveries might be coming next.
Totally. We've got new telescopes and experiments coming online all the time. It's like a golden age of cosmology, and the data we're getting, it's already challenging a lot of our old assumptions.
So where does all this leave us? What's the ultimate fate of the universe, according to the Big Bang Theory?
Well, that depends a lot on what dark energy turns out to be. If it stays constant, the most likely scenario is something called the Big Freeze.
A big freeze? That doesn't sound so good.
I know, right? It's basically the idea that the universe keeps expanding and cooling down, becoming more and more vast and spread out. Galaxies would drift farther and farther apart, stars would eventually die out, and the universe would, reach this state of maximum entropy, minimum temperature, cold and dark.
Okay, that's kind of bleak. But you said if dark energy stays constant, so could it change? Is there any chance things could go differently?
There is. I mean, it's all still theoretical, but if dark energy increases over time, the expansion could accelerate even more, leading to something called the Big Rip. In that scenario, even the fabric of space-time itself gets ripped apart.
Yikes, that's even worse. Are there any, more optimistic possibilities?
Well, there's always the chance that dark energy could weaken or even reverse its effect, leading to a big crunch. That's where the universe collapses back in on itself, maybe even leading to a new Big Bang.
So basically, we don't know if it's going to end with a whimper, a bang, or a rip.
Pretty much. The cool thing is, we're actively searching for those answers. Every new observation, every new experiment, it brings us closer to understanding these forces that shape our universe.
Well, listeners, that's a very deep dive into the Big Bang. We've covered a lot of ground, from the evidence for the theory to the crazy mysteries it still presents.
The Big Bang model, it's really an incredible achievement. It gives us this framework for understanding how the universe has evolved. But it's important to remember that it's still a work in progress. There's so much we still don't know, and that's what makes it so exciting.
Exactly. This deep dive, it definitely left me with more questions than answers, but that's what science is all about, right? It's about embracing the unknown and always searching for new knowledge.
Couldn't have said it better myself. The universe is full of incredible things waiting to be discovered. And who knows, maybe one of you listening will be the one to make the next big breakthrough, the one that solves the mysteries of dark matter and dark energy, and tells us how it all ends.
Until next time, keep looking up and keep asking those big questions.